When calculating for trusses, we need to calculate for two different forces. The external forces are provided by pins, rollers, or they are given in the structure. Pins usually look like a triangle and they provide two reaction forces. They are always perpendicular to each other. Rollers will either look like a pin with a circle around it or just a circle. These will provide one reaction force and it is always perpendicular to the surface. After you draw your external forces, you need to pick a pivot point. The pivot point is where you're going to measure everything from. And you write a sum of M, which is moments. Moments is equal to force times distance that are perpendicular to each other, and then sum of Fy and a sum of Fx. To solve for internal forces, you need to pick a joint. You want to pick the joint with the least amount of forces. Draw a free body diagram for the joint, and then write a sum of Fy and sum of Fx. If anything is at an angle, you need to use sine and cosine because you need to make them into x component and y component. In this class, we're going to solve for all the forces the physics method by accounting for direction as you go along. You can learn the engineering method later on when you go to college. This is one of the trusses found in activity 214. We're going to solve this the physics way to minimize error in sign. So first thing we're going to do is we're going to solve for the external forces. To solve for the external forces, we need to draw our external forces. There is an external force given at C of 50 pounds. B, joint B, is a pin, so there are two forces. I know the Y has to go up to oppose the 50 pounds. So this is BY. I'm going to draw my BX going to the right, but we could draw it in the opposite direction if we want. If the answer comes out negative, the direction is in the opposite direction. Joint A is a roller. You could tell by the little circles here. Rollers have one external force and is perpendicular to the surface. The surface is in this direction. We know it has to go horizontally, or reaction force. Since BX is going to the right, A has to go to the left to oppose it. After we draw our external forces, we must pick a pivot point. The pivot point is the point with the most unknown, which is point B. So pivot B. Next, we're going to write a sum of moment equation, sum of moment. Since there are three joints, there are three possible moments. One at A, one at B, one at C. This has to equal to 0. If it is not equal to 0, the truss will twist and end up breaking. Remember, moment is equal to force times distance, and force and distance must be perpendicular to each other. Since B is our pivot point, and we measure everything from the pivot point, the moment at B is equal to 0 because the distance is equal to 0. So now we're going to substitute in force of A, distance of A, plus force of C, distance of C. This has to equal to 0. Let's look at A. This is our pivot point B, and our A is going to the left. So if it goes to the left, this will rotate in the clockwise direction. Anything that is clockwise is negative. Anything that's counterclockwise is positive. This is by convention. So we know FA has to be negative. We don't know what that is, so that's going to be A times the distance. Since the distance have to be perpendicular to the force. Since the force goes to the left, perpendicular to it has to be up and down, which is 3 feet. Plus C, FC is given as 50 pounds. And so now we need to find D. C, the force goes down. My pivot point is to the northwest. Perpendicular to that is the horizontal distance. So that is also 3 from the picture. This is equal to 0. C, and this is my pivot point, and this is the beam. If I push it, this is going to rotate clockwise. So this is also negative. So now I'm going to solve. I'm going to move to the opposite side. So this is going to be 3A is equal to negative 50 times 3, which is 150 negative. So we're going to divide both sides by 3. So this a becomes a negative 50. Since it came out negative, I knew I drew my direction wrong. So the direction does not go to the left at a, it goes to the right. Once you have the direction wrong, you need to correct it immediately. So I'm going to go back to my picture and I'm going to redraw my horizontal vector. A is actually to the right. That means B, to oppose it, has to go to the left. So now we have A. Now we're going to solve for. Now we write a sum of Fy. Going up is positive, so that's going to be By. Going down is negative, so it's negative C. This is equal to 0. Again, all the forces have to equal to 0. All the moments have to equal to 0. If not, the truss will break. So I'm going to rearrange it. So By is equal to C, and C is 50 pounds. Since it came out positive, so I know I drew my direction right, By is going up. Now I'm going to write a sum of Fx. My sum of Fx, A is going to the right, so I'm going to make that positive. Bx is going to the left, so it's negative Bx equals to 0. So Bx is equal to A, which equals to 50. Came out positive pounds, so my Bx is in the right direction. So now we solve for all the external forces. So now that we solve for all the external forces, we're going to solve for our internal forces. I just drew the external forces on there and labeled properly. So it doesn't matter where you start, but you probably want to start with the one which has the least vectors on your free body diagram. So I'm going to start with joint A. So the first thing I'm going to do is draw my free body diagram. That A goes to the right. I solved it at the top. So that means AC must go in the opposite direction to oppose it. And if I look at AB, it really doesn't matter which way I draw it because there's only one vector. I'm just going to make it go to the top, which is AB. So for internal forces, we only write a sum of Fx and a sum of Fy. So my sum of Fy is going to be AB is equal to 0. So that means the AB is a useless beam. It's a waste of money. You don't need it. It has no effect whether you have it or not for the truss to work. My sum of Fx, I'm going to make going to the right positive. So it's A minus AC, because AC is going in the opposite direction, equals to 0. So AC is equal to A, which is equal to 50 pounds because we solved this in the previous page. So our direction is correct. It is going to the left because it came out positive. So now I'm going to label the direction of the force on the beam itself. So we know AC is going to the right, so I'm going to make this AC go to the right. Next, I'm going to move to joint C because joint B has extra forces. So I'm going to draw my free body diagram for joint C. So again, we know C has to go down because that was given. AC, we already solved it. We know that the force goes to the left. When we are at joint C, it must go to the right to oppose it. Forces on a member or a beam must go in opposite direction. If not, they break apart. AC went to the left, CA must go to the right. So if I look at CB, there are two ways I could draw this. It could go northwest or it could go southeast. Since we already have a vector going south, to oppose that south vector, we need a vector in the north direction. CA we know goes to the east, so we need a vector that opposes going in the opposite direction, which is west. So the only possible direction for this member is northwest. So this is CB. Again, C is going south. To oppose south, we need a vector going north. CA is going to the east. We need a vector going to the west in order for this to be at equilibrium. Since vector CB is at an angle, we need to resolve it into x and y. So we're going to make a right triangle. This is CB. This is my theta. This is my right triangle. So opposite the angle is going to be CBY. So this is going to be CB sine theta. Adjacent to the angle is CBX, which is CB cosine theta. So I'm going to redraw these vectors in to help you out. So if I redraw joint C, what it actually looks like is CA. We have C, we have CBY going north, and we have CBX going to the west. You would never draw components in a free body diagram for physics, but I redrew it here to help you out. After I make any vector at an angle into x and y, I'm going to write a sum of Fy. CBY is going north, so I'm going to make that positive, minus C, which is going down. This is equal to 0. I'm going to substitute in for CB, which is CB sine theta, minus C equals to 0. So CB sine theta is equal to C. We're going to divide both sides by sine theta. So CB is going to be C divided by sine theta. And what is theta? If I look at my picture, so my theta, this is 3 feet. This is my angle I'm looking for. This is also 3 feet. So how do I find this angle? Tangent theta, which is opposite over adjacent. Opposite the angle is 3 feet. Adjacent is also 3 feet next to. So this becomes theta inverse tan, which is 3 divided by 3. This becomes 45 degrees. So if I substitute in, C is 50 pounds, sine 45 degrees. This becomes 70.7 pounds. And since it came out positive, I know my direction goes northwest. So I'm going to draw my directions in. So here, they're opposing each other. At joint C, it's going up. So that means at joint B, it has to go down. And then this one, we solved that it is not necessary. Since we solve for everything, we don't need to do joint B. When you solve for trusses, you do not have to do the last joint. You will always solve all the unknowns before you get to the last joint. The last thing we do after we label, we need to see if these are in compression or tension. So we look at joint A. If I look at joint A, AC is pushing into joint A. If I look at joint C, CA is also pushing in. When it's pushing in, these are in compression. It's compressing it. Now I look at joint C again, and I look at CB. CB is pulling away or going away. At joint B, BC is going away. So these are in tension. So again, we do the external forces first using moments, F of X and F of Y. Once we find the external forces, we do internal forces by drawing free body diagrams of each of the joints. And once you solve for all your unknowns, you are done.